Welcome, students. Today we're going to talk about factoring expressions in quadratic form. And we're going to start with a definition. A quadratic polynomial is a second-degree polynomial. So basically, any polynomial that can be written in the form ax squared plus bx plus c. Now, it might be possible that b or c is equal to 0, so we might not have all three of these terms, but it does have to have the x squared term for it to be considered quadratic, because if a was 0 and this term went away, it would be a first-degree polynomial. So we're basically looking at things in this form. Now, today we're going to be factoring expressions in quadratic form. What that means is we're going to be factoring expressions that are kind of related to this, but not exactly like this. Let me show you an example exactly what I mean. Let's factor the quantity 3x plus y squared plus 7 times the quantity 3x plus y plus 12. This is more complicated than anything we've factored before because we have binomials inside of parentheses, and in one case that binomial is being squared. Now, there's a couple of ways that we could potentially go about this. You might think to actually go through and multiply this out and distribute the 7 and then combine like terms and try and write it without the parentheses. But that isn't the best way here. In this situation, the parentheses actually help us. Because if we ignore what's inside the parentheses for a moment, if we just look at this as something squared plus 7 times something plus 12, this kind of looks like something that's quadratic. We have our first term that has something squared. The second term has that same something with a coefficient, and then the third term is a constant. So there are ways in which this big expression is very much related to a quadratic polynomial. It's just more complicated. There's two variables and there's parentheses and whatnot. What we can do in a situation like this is we can make a substitution to make things simpler so that what we start off with looks a lot more like what we want it to be. If we replace the things in these parentheses with a single variable, in this case we're going to choose z, then this does end up looking like a quadratic polynomial. That's the method that we're going to use in these situations. We're going to make a substitution to make it look more like a quadratic polynomial. The variable we use most often in this case is z for our substitution. We can't use x or y because x and y are already represented in this problem. And z is just the default someone chose a long time ago. I'm horrible with mathematical history, but they chose it, and that's typically the variable that we use in these situations. So let's make this substitution and then see where we can go from there. The substitution we're going to do is we're going to let z be equal to 3x plus y. Now, wherever we see a 3x plus y in the original expression, we can replace it with a z. So this first 3x plus y is going to be z. So that's going to be z squared plus 7 times, and again, that 3x plus y gets replaced with z plus 12. By making this substitution, we've taken something that was relatively complicated and we've rewritten it as a quadratic polynomial. And at this point, we have something that we do know how to factor. We can use unfoiling here. We're looking for two numbers that have a product of 12 and a sum of 7. Can you figure out what those numbers are? They're 3 and 4, because 3 times 4 is 12, and 3 plus 4 is 7. So when we factor this, we get z plus 3 times z plus 4. But this isn't going to be our final answer. In the original expression, everything was written in terms of x and y, so we can't have an answer that's written in terms of z. How can we rewrite this back in terms of x and y? Well, we can take the z's and replace them with 3x plus y's. So in this first one, that z becomes 3x plus y. So we have 3x plus y plus 3 times 3x plus y plus 4. And that ends up being our final answer. It would have been incredibly difficult to get this answer without going through the process of making the substitution. If we instead tried to get rid of the parentheses by distributing the 7 and by squaring this expression, we would have ended up with something with lots of terms, and it would have been too difficult to factor. But by making this substitution, we end up with something that is not that bad. Let's do a couple more examples. Next, let's factor, and where is my example? 2 times a minus b squared plus 5 times a minus b minus 3. Again, we have something that's relatively complicated, but we still have a first term that's got something squared, and a second term that has that same something, and a third term that's a constant. So we should be able to make a z substitution so that this all becomes simpler. What are we going to let z be equal to write this in a more simple way? Well, just like the first example, we're going to make the substitution where z is the thing that's in the parentheses. So let's make that substitution. We'll let z be equal to a minus b. And when we do that, we can rewrite this as 2z squared plus 5z minus 3. Now we have a quadratic polynomial, and we can factor it. We're not going to be using the unfoiling method, though. Why is that? Well, this one is different. It has a leading coefficient, so we have to use the AC method. In this case, a times c, 2 times negative 3 is negative 6, and b is 5. So we're looking for two numbers that have a product of negative 6 and a sum of 5. Those numbers are 6 and negative 1. We're going to use those to split that middle term. So we're going to rewrite this as 2z squared plus 6z minus 1z minus 3. And now that we've done this, we have 4 terms, so we can finish by grouping. In the first group, those two terms share a 2z. So we can pull out 2z, which leaves us with z plus 3. In the second group, we can pull out a negative 1, and that also leaves us with z plus 3. So then the groups have a z plus 3 in common, and leftovers 2z minus 1. Now there's one more thing we have to do. We cannot leave our answer in terms of z if the original problem was in terms of a and b. So we're going to have to go back and substitute in wherever we see a z here, we're going to have to replace it with a minus b. So this first one is going to be a minus b plus 3. And then the second one we have to be careful because it's not just z but 2z. If z is a minus b, then 2z is going to be 2a minus 2b. And then minus 1. And this is our final answer. This method of making a substitution allows us to factor things that we could not have factored otherwise. This is another tool that we can use to broaden our abilities as far as factoring is concerned. Now I want to do one more. This one's going to look a little bit different, but we can still use the same method. Let's factor, and let's do x to the 6th plus 10x cubed plus 21. This is different from the other examples in a couple of ways. First, there's no parentheses in this expression, so it's not clear immediately what substitution we need to make. The other thing that's different is that we've got higher powers here. This is a 6th degree polynomial. That said, it still looks similar to the quadratic polynomials we've looked at because we still have 3 terms. One of them is constant, and if we look at the variable parts of these terms, one of them is equal to the square of the other one. In fact, we could rewrite this as x cubed squared plus 10x cubed plus 21. And if we do that, then we recognize that the substitution we need to make is z equals x cubed. So let's let z equal x cubed. When we do that, this becomes z squared plus 10z plus 21. The reason this worked is because x to the 6th is the square of x cubed. This would also work if it was x to the 4th and x to the 8th, or x to the 5th and x to the 10th. In either of these situations, we've got something in quadratic form, and we can rewrite it as a quadratic polynomial by making a substitution. Now that we've made the substitution, we can use unfoiling here to factor it. We're looking for 2 numbers that have a product of 21 and a sum of 10. Those numbers are 7 and 3. So this becomes z plus 7 times z plus 3. And then when we go back and substitute in the x cubed for z, this becomes x cubed plus 7 times x cubed plus 3, which is our final answer. This even works in other scenarios, but for right now, these are the only ones we're going to look at. There are more examples, though, in the videos linked below, so please get some practice there to help you prepare for your homework.